Have you ever looked at an optimization algorithm and just felt overwhelmed? Like you need a special degree just to figure out all the settings? Well, today we're looking at something different. It's an algorithm called Jaya, and it's built on a radical idea. What if the best solution was also the simplest? Let's dive in and see how it works. So, to really get why Jaya is such a breath of fresh air, you have to understand the world it was born into. For years, optimization has been full of these brilliant but super complicated algorithms. Think of it like being handed the keys to a Formula One car, but the dashboard has 1,000 different knobs and dials, and you have to get them all perfect just to get off the starting line. And this slide just lays it all out. Plain and simple. On the left, you've got the usual suspects. Genetic algorithms, particle swarm optimization, you name it. They all come with this long list of special parameters you have to tune. Then, on the right, you have Jaya. And its big revolutionary idea? No special parameters. I mean, none. Zero. It's designed to just work, right out of the box.
So let's talk about this maze, this jungle of parameters that Jaya was designed to clear a path through. And make no mistake, getting lost in there is a real problem. If you don't tune those parameters just right, you could waste a ton of computer time, or even worse, end up with a solution that's just flat out wrong.
And just look at how specific this stuff gets. For a genetic algorithm, you're trying to guess the right probability for mutation. For particle swarm, you've got things like inertia weight. And my favorite, with an artificial bee colony, you literally have to decide on the number of onlooker, employed, and scout bees. How on earth are you supposed to know that? It's a lot to ask. But what if you could just skip all that guesswork? What if there was a more direct path to the solution? Well, this is exactly where Jaya enters the picture. It offers a totally different approach, one that just gets rid of all that extra baggage. The name itself really tells you everything about its purpose. Jaya is a word from Sanskrit, and it simply means victory. The whole point of this algorithm is to win, to find the best possible answer to the problem, period. And this quote right here is the entire philosophy in a nutshell. It's so beautifully simple. It's not trying to mimic nature, like bees or evolution. It's based on this one universal idea of how to get better at anything. Try to be more like the best, and try to be less like the worst. That's it. It's just common sense. Now, you might be thinking, okay, that sounds great in theory, but how does it work in practice? How do you turn that into code? Well, that's the truly elegant part. That whole philosophy is captured in one single powerful equation. And here it is. This is the engine that drives the whole Jaya algorithm. Now, I know it might look a little intense at first glance, but let's break it down, because the idea is actually incredibly simple. All this equation does is tell us how to take any current solution, x, and update it into a new, hopefully better solution, x prime. Let's look at the first piece. This part right here is all about attraction. It creates a pull, a sort of gravity, that nudges our current solution in the direction of the very best solution we found so far. That R1 is just a random number to vary the size of the nudge, which helps keep the algorithm from getting stuck in one place. Now for the second piece. If the first part was a pull, this part is a push. It's all about repulsion. It looks at the absolute worst solution in the group and shoves our current solution away from it. And again, R2 is another random number. So you get this simple, elegant dance. Get closer to the good stuff and get further away from the bad stuff. And that elegant logic translates into this dead simple 5-step process. You just start with a random bunch of potential solutions. In every round, you find the current best and the current worst. Then you use that equation to update everybody. If a new, modified solution is better than its old version, you keep it. And then you just repeat. That is the entire algorithm. All right, theory is great, but seeing is believing. So let's watch Jaya work its magic. We're going to walk through a classic benchmark problem called the sphere function, using the exact example from the original research paper. So our mission is simple. We need to find the inputs for the sphere function that get the output as close to 0 as possible. For this little demo, we're going to start with a population of just 5 candidate solutions. Okay, so here's our starting lineup. These are our 5 random guesses. If you look over at that f of x column, which is basically the score, you can see our best and worst right off the bat. The best is candidate number 4 with a score of 113, and the worst, well, that's candidate 3, way up at 4,936. Those two are now our North Star and our warning sign. Okay, now we hit go for one round. We apply that Jaya equation to all 5 candidates, and here are the results. A few of the solutions got better, so we updated them. Our best solution is still that same one at 113 for now, but look, our worst solution has already improved a lot. The algorithm is already pulling the whole group in a better direction. And now for iteration number 2. This is where it gets really cool. Remember candidate number 1? Before, it was just kind of in the middle of the pack. But after getting pulled toward the best and pushed away from the worst one more time, bam! Look what happened. It took a massive leap forward and is now our brand new best solution. And this is the number that tells the whole story, 7.7803. We started with a best score of 113. In just 2 simple steps, we got it all the way down to under 8. That is a huge improvement, and it just shows the raw power of that simple push-pull logic. So obviously, this is more than just a cool math trick. Having an algorithm that's this simple and this effective has some pretty big implications for solving real-world problems.
And you don't have to take my word for it. The data speaks for itself. This chart shows the results of a statistical test that ranks algorithms against each other on a whole bunch of different problems. Lower is better. And as you can see, Jaya consistently comes out on top with the #1 rank, beating many of its more complicated competitors.
So why does all this matter? Well, because optimization is absolutely everywhere. It's used to design more efficient engineering systems, to streamline scientific research, you name it. Jaya gives people in all these fields a really powerful tool they can start using immediately, without needing to be an expert in tuning parameters. Which really leaves us with this one big final thought. The success of an algorithm like Jaya forces us to ask a pretty important question. In a world that seems to get more complex every day, where we often think complicated problems need complicated solutions, could it be that the real advantage, the ultimate victory, actually comes from simplicity?